Can you guys hear me?
Yes.
All right, okay. Yeah, we survived the whole quarter without having technical issues, but until the last lecture, I guess. Okay. So it's good if you guys can hear me. Okay, so the goal for today is basically to finish looking at power system markets. Then we'll go into, we'll do a brief review of all the topics we cover, essentially in the after the midterm, right? And think about, what kind of type questions that may be on the final. Okay. All right, so as a reminder from last time, basically for markets, what we said is there's two types of power system markets. So there is an example of a pooled market. And for these pool markets, what we have is basically we always have an operator. We always have an operator. And the supply and demand never directly negotiate with each other. So the supply and demand, basically supply talks to the operator. And the demand talks to the operator. And what ends up happening is it's up to the operator to come up with a schedule or to match supply and demand. Okay, so this is very much a matching market. So this is a okay, so that's very much up to the operators to do this. And then if you look at another example of markets, it comes from so-called bilateral trading, because bilateral trading says that the supplier and the demand should talk to each other directly. The bilateral trading says they should talk to each other directly. So there's a sort of negotiation. Okay, so they can directly talk to each other and figure out, how much you want to sell, how much you want to buy, and what the, at what price and what level. So there's sort of two ways of looking at this kind of markets. Okay. So the US operates by basically as a pooled market. Okay. And in Europe, it's more a bilateral trading. It's more bilateral trading. So the pooled market is actually becoming more common. So when this was first talked about in the US, basically in the late 90s and early 2000s, was a very weird market. Because at that time it was uncommon to have, some central platform essentially sitting there, and to not have, the supply and demand talk to each other. But this is becoming a lot more common now, right? So what's another example of a pool market where you only talk to the platform and never the sort of the supplier? So in your lives, in our life, think about what are the sort of the examples of pooled market. Quite common nowadays. In other contexts? That's before the pandemic. We used this quite a bit. Right? So if you think about something like Uber or Lyft, that's essentially a pooled market, right? So in Uber, you never, shop around for the drivers directly. You talk to the platform, and the platform matches the rider with the driver. Okay, it's not a choice. You typically don't have choices of picking specific drivers, right? You enter destination, and the platform tells you, okay, so and so will come and pick you up. Okay? So this is an example of a pooled market. You talk to a platform, right? Then in comparison, something like going to different restaurants, that's a bilateral trading essentially. You pick the specific place you want to go, and you can negotiate where to go. Okay, so pool market was uncommon. In the early 2000s, wasn't a lot of ride sharing, and there was no ride sharing at that time. So it's a very uncommon market. But nowadays, it's a lot more common. Right? Anytime you're doing ride sharing, or anytime you have sort of share resources, it's very, very common nowadays to talk to the platform instead of talking to the physical provider of the goods per se, right? So this is where the market is going. And if you look at a lot of the early literature for how ride sharing works, a lot of actually the insight actually comes from how power market works. Basically, you have an operator. What is the role of the operator? How should it do matching? Things like this. There's quite a sort of bit amount of commonality in this kind of markets, right? Where the platform plays a central role, and it's up to the platform to do matching. So again, this happens quite a bit in. I guess another good example you can think of as matching, for example, placement in for medical, right? So when you go to medical school, after that you do a residency. For medical residency, there's a matching system like this. There's a lot of schools that start to do matching instead of you directly picking. There's a central platform that tries to match supply and demand. Right? So there's quite a bit sort of example of this nowadays. And you can think of power system as one of the sort of the very early example of this sort of matching markets. All right, so let's look at one example of this sort of pooled market, pool trading, so on. So pool trading basically this is actually quite close to what happens in practice. We'll have pool trading. So pool trading is, first of all, we build up this table. Okay, we'll build out this table. And you build out this table, basically you have bids. So in power system, jargon, bids means generators. Offers come from loads. Okay. So bids is what the generator says is willing to supply at different cost. And the offers is what the load says is willing to buy at different cost. Okay. So different quantity versus price. So for example, if you look at let's say you look at this generator, so this red generator, what is basically offering is the following. So this is the quantity, Q, this is the price. Okay. So what that is for the first 200 megawatts, you have you have a lower price. And the price goes up. This is the first 200. This is next 50. This is the next 50 megawatt going up. Okay. So basically, the offers, the bids are increasing function, right? As the cost gets more, as the production gets higher, it's more expensive to produce power. So you have this bunch of bids, and you collect this bunch of offers, and you basically try to balance the market. You try to balance the market. So go ahead. Question.
Professor, can go to the slide up. So for the one is like the generator, so the base one, like so the company, it's called 200, and the price is $12. So, but there's the 1, 2, 3, 4, 5, 7 companies here.
There's 3. Sorry, I think I missed a question.
Oh, there are 3 companies, right? The one company, green, another company, blue, company.
Sure.
So the price change like the $200 to $12. So with actual $50, the price is 15. And
so it builds up this curve, right? So for which company, basically builds up an increasing curve.
Okay.
So for the first 200 megawatt hour, the price is 12. Then if you want 50 more, for the next 50, the price is 15. And for the next 50, the price is 20.
Okay. Okay.
Yeah, so you build up this kind of curve, basically.
Professor, I've got a real quick question too.
Sure. Go ahead.
The load,
Mhm.
who is giving those offers? I assume it's not like I'm also the load, but I'm not.
Your utility is giving this offers. So City Light, yeah, City Light is doing so. You can if you're in the market, right? So nowadays, actually, getting into the market is not very hard. So if you're reasonably large load, you can make offers if you want. There is a sort of barrier for entry, right? You cannot be a 1 megawatt load. But nowadays, if you're say, a few hundred kilowatts, you can be in the market. So this, you can think of this, being a utility, but also you can think of this being a building. Right? If you're a building manager and you want to play this game, you can provide offers if you want. Yeah, so again, we think of bids as generators, offers as load, in the sense that bids are things that basically provide power. Offer are the things that consumes power, right? But this can be of different size, and they can be speculators as well, right? So for example, you don't actually need a physical generator to play in the market. Okay, if you think you can, buy power in some other way, maybe you bought power through bilateral trading, and now you want to play in the pool spot market. You can go in as a bid or a offer, right? So these are just, think of bids as providing power, offer as consuming power, but they can be physical quantities, they can be utilities, or they can just be speculators in the system. That there's virtual entities that with no physical assets. These are there are quite a number of these entities in the market. Okay, so this is the bid and offers. So at a sort of very simple setting, clearing the bids and offers is not very difficult, right? Basically, the way you do it is you line up bids and offers. So these are the offers. Okay, so these are the offers. They're decreasing, right? Because that's okay. For a small amount of quantity power, I really need that power, right? I'm a load, so I really need some power. So I start at a high price. Then as the price goes, as the quantity goes higher and higher, I need this powers less and less. So it's a decreasing function. As price is a decreasing function of quantity. Then if you look at the bids, right? So it's cheaper to generate power at the beginning and gets sort of progressively more expensive as the quantity increases. So it's an increasing function. So offers are decreasing functions. But this is increasing. So eventually they will cross at a point. And this point basically is when the amount of the price of the offers matches the price of the bids. And this is the market clearing point. Right? You basically, this point determines the quantity and the price at the end of the day. Right? So if you cross these two curves, you basically have this is the quantity we have decided, this is the market price we have decided here. All right, so this is one example where clearing the bids and offers is quite simple. You stack up all the offers, you stack up all the bids, you look at where they cross, and this determines the quality and the price. Right? And a sort of vastly more complicated version of this goes on, every hour of every day in the US, basically, to figure out to clear the market. Right? It's much, much more complicated because we have transmission constraints, we have unit commitment constraints, we have a very large number of bids and offers, things like this. But at the end of the day, it's just this process. It's basically you stack up the bids and offers, and you look at when the two curves cross. All right. So any questions with this basic process?
I've got.
Market. Yeah, go ahead.
I'm a little confused on how the crossing point establishes the quantity traded, because isn't that decided by the demand?
So the demand is, so the offers determine the demand, right? So in this case, we have a flexible demand. So the demand is not a straight line, right? So if you look at the offers, these offers are basically saying the following: I'm willing to pay this much for a certain amount of power, right? So this is not a fixed demand. The offer sets the demand in the system.
Okay, that makes sense.
Yeah, the offer sets the demand. So this is the market, right? So for the physical delivery of power, we are going to meet demand. But think of this as how the financial system works. Okay? So City Light basically has to buy some amount of power. And City Light is not, City Light doesn't know its demand perfectly for the next day. So it will be some wiggle room. Right? So in this example, we have a lot of wiggle room for the demand. In practice, this is sort of much narrower range of demand we can operate in, but there's sort of some, small rooms we can switch around.
Okay, so like another way to think about this is that crossing point kind of sets the demand also.
This crossing point sets the demand for this certain bids and offers, right? Okay. So this sets it. So this put trading is normally done at some time ahead of the actual physical delivery, right?
Okay.
So we're doing, for example, for next day, this sort of market clearing happens now for tomorrow, for Thursday. So we decide, how much demand is the demand for tomorrow and so on. So the actual demand for tomorrow is slightly different. So we run another spot market to clear that. So the sort of markets on top of each other.
Okay, sure, thanks.
Yeah, so that's sort of the very standard matching supply and demand. Any other questions about this? Okay, good. So we can look at this slightly more. We can look at this a bit more closely. So if you look at the so if you look at the market clearing, so let's just look at the suppliers in this case. Okay. So we have something like red, blue, red, green. So this is the market price. Okay, this is market price. This is the quantity. This is quantity. So if you look at the price, market price and quantity, right? You look at the market price and quantity. How much money does the generators make? Right? So the question is, how much money does the generators make? Basically, what happens for the generators, let's say you're red, right? So if you're let's say you're the red generator for the first block. So this is your cost of generating power for this block. Okay. Your revenue is actually, right? So this is the profit. Okay, this is the profit for the generator. So if you once you do this kind of market clearing, right? So the total payment made by the offers, by the load, is the market price multiplied by the quantity. Okay. So that's the total sort of money the consumers pays into the generators. Then the way the generators makes money is you basically look at your cost, which is area under the curve, and your profit is the area above the curve, up to the market clearing price. This is sort of how money are made in the system. Okay, so any questions about this? So this is, so if you know, this is how monies are made. This is how money exchange hands. So if your generator, what you hope for is basically you're hoping that the market clearing price will be higher than your own price than your production cost, right? So the market clearing price is higher than the production price, then you end up making some money. Right? You're making this chunk of money basically above the curve. Right? So of course, you know, it's hard to say when. So it's hard to predict how much this gap is, but the hope is you always, you know, be some sort of gap like this, and you can make money. Okay. All right. So if you adopt this strategy, would a generator ever lose money? Right? If we adopt this strategy, would a generator ever lose money? If you look at this kind of market price clearing. So if you're clear, right? If you're used in this kind of market clearing, do you ever lose money? Right? So this actually shows that the generators never lose money. So the bids never lose money. If the bids are cleared, you never lose money, because if you're cleared, your price, your production price will be under the curve, will be under the market price by definition. Okay? So if you're under the market price, there will be some gap between the market price and your production price. So this way that you don't actually, you know, lose money. You don't lose money. Okay? So why is this a good strategy? So why do we do this? Why do we set it such a way that the generators will not lose money? Right. So why is this sort of? There are other ways we can choose to clear the market. Why do we clear this way? Why do we sort of specific structure in such a way that the bids, if cleared, cannot lose money? Any reason for this? Should we do? Is there another way to do this, or why do we? So this is a very. So this choice was this is a choice made by the people designing power markets. So why do we make this choice? It's really so to keep the bids low. So it's not necessarily to keep the bids low. This choice is made to keep the bids to make sort of give generators incentive to not lie in their bids, to not lie. Because if we adopt this practice of, you know, everything under the market price is a profit, then if the generators have low bids, right? If the generator have low cost, there's no incentive to lie about their cost, right? As a generator, you want to be in the market if your cost is low. So you will not lie about your cost being, you know, artificially high. Similarly, if your generator with a high cost, you will not lie about your cost being artificially low, right? There's no reason to lie in this case, right? So this choice was made such that the generators will be incentivized to provide truthful information. Okay, so we can make decisions using true information from the generators, right? So because this is, this is the market. So as a platform, as an operator, I don't know the true cost of the generators. So if we clear the market this way, then there's some incentive for the generator to actually tell the, the planner, the central operator, their true cost of doing business. So there's no incentive to lie. We do it this way. Now, this sort of makes a lot of economic sense, but in practice, it's not always as simple. But there's sort of the fundamental economic reason to do this is just to make sure people just give the true price. Okay. Whether this happens in practice or not is debatable, but at least from the market we just choose to structure market this way. Right. So this is again an example of the bidding market where your amount of where you have a central operator where you tell the operator you offer some bids, right? The operator never asks you to guess what the clearing price is. So this is different than sort of the common auction you'll see, right? This is where you just, in principle, you tell the operator the truthful information, and the operator clears the market for us. Okay? So this is at a very, very simple level how power systems, how markets are cleared in the US. Right. So, what makes things harder is basically it's not just one market we have to clear. There's unit commitment issues, right? So as you have seen, from the homework, we always need to think about what happens when we have multiple time periods and multiple generators. And we cannot clear a market, just at the separate time periods, totally independent from each other, essentially because generators cannot be shut down, cannot be turned off, on and off arbitrarily at each time period. All right, so we have unit commitment, so we have operating constraints. All right, so we have, mean up, mean down times. We have ramp rates on the generators. We have startup or shutdown cost. Okay, we have, so all these costs are basically in the system. So this says this, we cannot just treat each hour independently. Okay. So what happens is basically this sort of pool trading runs on top of a unit commitment program. Okay, so it's not a purely you give offers, you give bids. Basically, since we have all these operating constraints, we essentially have a unit commitment program sitting in the middle. So the central operator runs a unit commitment program. And what takes in is we'll take load forecast, we'll take bids, we'll take offers. What gets out is a schedule, a generation schedule. And then this determines prices. Right, so in actual practice, this were very simple, just crossing two curves. It's more complicated, and the actual, clearing process is basically a unit commitment program. They're just running a unit commitment program. Okay. So any questions with this? Okay. So for those people who's interested in the economic theory of this, the bad thing is the unit commitment program destroys all the nice econ theories we have, basically. Because we need to run unit commitment, this thing wipes out all the nice theory about the property of the market we should have. Okay, so a big thing today that system operators who's clearing the market think about is how to more gracefully merge unit commitment with the nice economic theories that we want to have. Okay, so if you look at actual practice, there's power system engineers who cares about the systems, operating the system reliably and securely. There's the economists who think about how the market should work, and getting them to talk to each other is not always trivial. Okay, they're not, they don't always play nice with each other. What stops someone from buying a cheap generator from Home Depot area like California? So in the chat, when they have a rolling blackout, charging $1 million per watt. So in principle, nothing stops people from doing this, right? So for example, this is fine. Right? If you believe the market, if you believe the price should reflect the demand for power, then you can do this, right? So there's nothing preventing you from doing this. If you did not create the rolling blackout, it's completely, it's completely legal to do this. There's no problem with this. So there's some questions whether you can make money or not, right? The question is, one, California has a price cap. Okay, so cannot go to $1 million, right? There's not a, cannot go to $1 million, can go fairly high, but not arbitrarily high. So in the systems where you have a cap, the issue is that you can buy a generator. There's actually a good amount of operating cost with generator and maintenance costs and so on. So whether you can time the system correctly to make this much money, to make factory investment, is not trivial because you don't know when this will happen. Right? So keeping a diesel generator always on standby in case this happens, you actually don't make enough money out of it. So in a system without a cap, for example, Texas has no cap, this is more doable. Although you still need to be careful that you can time the market correctly, right? You still need to be even more careful about where you are in the system, so on, right? And basically, there's many people trying to do this using batteries. Okay? So the holy grail of using batteries to make money in the system is essentially to time the system. So you can charge the batteries when the prices are low, hopefully negative, and you can discharge the batteries when the prices are very high, hopefully $10,000 per megawatt. Right? So this is the holy grail of using batteries in the system. There's many startups trying to do this. I have worked with startups trying to do this. And the key always comes down to it's very, very difficult to time this correctly. Okay, this is sort of not trivial to time this. It's not trivial to time this. Right? But in principle, there's nothing stopping you from doing this. Okay? This is the legal. There's nothing illegal about this. Right? Right, and that's why there's significant trading volume for energy. So this actually, you think of people trading in commodity markets, right? People trade, gold or core or wheat, whatever, and there's a significant amount of people trading energy. There's so I have met, if you go to City Light, there's a trading desk in Seattle City Light whose whole job is to trade energy. Right? So this is fine and it's legal. So it's not necessarily bad if you want to make money from this. Right? Okay, so any other questions about this sort of commitment and pool trading? Okay, so there are some other practical issues or practical constraints with this, right? So basically, following up on the question of what's stopping people from making money when there's not enough supply. That's fun up until if you're having collusion, right? So if you are causing blackouts and trying to make money from blackouts, that's not allowed. Right? This is basically the Enron, what happened with Enron in the early 2000s from the California energy crisis. It's basically as long as you do not collude, then it's fine. Right? So one constraint is all units need to bid separately. Okay, you cannot all collude together and try to access market power and try to create blackouts when there is not a blackout. Right? So you have to. This is one. It's a legal requirement. Basically, you have to bid separately. Okay. And then they also a requirement. So this is a computational requirement actually. Well, the computational requirement is your bids have to look something like this. So your bids has to be piecewise linear. So this is whether your actual generator cost looks like this or not, you're required to bid a piecewise linear increasing function so that unit commitment can be solved. Okay, so this is required. You have startup price, you have shutdown. And you have sort of a bunch of parameters, right? So again, the thing is you can bid as long as you follow these two rules. You have no collusion, and your bid follows this format. Then the bid does not have to have anything to do with your cost. Okay, there's not necessarily you can bid whatever you want as long as follow these two rules, right? And bidding very low, right? For example, you can get into the market by bidding very low. That's fine. If you don't want to be in the market, you can bid very high. You can try to guess the price if you want and bid, close to that price. All of this is fine. Right? There's only basically the big rule is don't collude with other people. Don't access market power. Okay? So that's the number one rule in the system. So one question is, how do you figure out if people are colluding or not? How do you figure out if people are cheating the market? Right? How do you figure out if you and me, we have two generators, we say, hey, let's tell the system that our generation is lower than we actually have them to create some high prices, and try to make money because we are pushing the system close to blackout. Any ideas how to detect this? Right, so this is the rule, right? The rule says you should not, collaborate with each other, but that's part of the rule and they're part of enforcement of this rule. So any ideas how to detect this? Okay, so this is actually one of the hard problems in power system operations. There's not really a simple way to tell when people are doing collusion or versus, the system just happened to be this way. So the way this is dealt with in practice, you have each operator will have a large team looking at the bid. So a lot of this by human intuition, people will look at it and try to see whether they think there's collusion or not between different generators. And another way you prevent people from doing this is when you actually buy and sell a generator, you cannot hold too much generation capacity. So there's a monopoly rule here, meaning that not a single company can go in and buy all the generators, right? So for example, in Seattle, let's say Amazon wants to make money and say, okay, I'm going to buy all the generators in Seattle and I'm going to charge the price, $1 million per megawatt, right? So that's not allowed. So one way is you prevent people from buying too much generation. Another way is you have humans looking at this. But it's it's a challenging thing. It's a challenging thing to make sure this doesn't happen. And I have a friend who works in FERC, basically the regulatory body who's in charge of this. And they say basically, they try to scare people. So if they think there's collusion going on, you'll send 100 lawyers to the company and try to say, okay, don't do this. We think there's something going on. Don't do this, or we catch you. They can impose pretty heavy fines. Okay, so there's sort of different mechanisms. But if you guys are interested in, for example, going to an operator or looking at trading and things like this, how to detect market power is not trivial at all. And nowadays we're putting storage into the system. And how to detect market power, for example, exercised by storage, is again tricky. Right? It's a tricky thing. But so that's something to think about. So ideally nobody should collude, but in practice, how do you detect this? Is a sort of very interesting. Actually, if you work on this, so your job will be quite interesting to try and figure this out. So it's an interesting topic. And so another thing we have is in this picture is when we look at load, we'll look at load forecast into the unit command program. And this is also why it's not easy to time the market when the price will be very high. Because what happens is the system is doing load forecasting. So load forecasting, basically, let's say you're doing this a day ahead. A lot of times the forecasting is pretty good. So we'll make sure we have enough generation capacity for the forecasted load, right? So it's not necessarily when the load is high, you will see sort of super high spikes in the price. When load is high, we will have more generation, and this will cause a higher price, but not necessarily a lot of spikes. Right? You will see spikes when the uncertainty is high. So if the load forecast can be done, fairly accurately, then at least there should be enough resources in the system, right, to cover the load. Okay? And the typical load forecast looks something like this, right? So you have this is normally the evening peak. So this goes from 5:30 to 8:30. When people are home, they're watching TV, they're cooking dinner, things like this. Most systems you see this kind of peak. And then you schedule generation to satisfy this kind of peak. Right? So basically your generation schedule is you stack generators, right? You have the cheapest one, the more expensive one, so on and so forth. You stack them and you meet the load, right? And if you look at this kind of generator schedule, the interesting thing about this schedule is you will always have this kind of marginal units, right? So marginal units means the last unit you used to satisfy the demand. It means last unit you used to satisfy the demand. Right? So these are the most expensive unit we used to be able to meet demand. So the thing about marginal units is the marginal units basically sets the market price, right? So this is the last unit used, and then its price is equal to the clearing price. Right? So this is the most expensive one. So if you think the supply curve going up, so the last one that gets used, that's the price. Okay? We're basically setting the market price. Okay? And then everything is traded at this price, right? As we talked about before, so everything is traded, at this price. Okay? So the thing about trading at this price, I always talk about if you have a supply curve. If this is our supply curve here, and this is the clearing price. This is the single price we see. Okay, so we buy and sell at this single price, right? And the idea is to say that, so cheaper generator do not can be truthful, right? So they're not leaving money on the table just because they're cheaper generation. Okay, so they can bid their truthful price, knowing that the final price is set by the marginal unit. So there's no guessing. So ideally, you don't need to guess a clearing price. Although in practice, there's still people guessing at what this price is, right? So, but ideally, there should be no need to guess this, right? So this is why everything then is bought and sold at this price. All right. So, any questions about this or pool trading for electricity? Okay. So the whole thing gets much more complicated once we have things like batteries, renewables, and all that, right? So really the market for when we have renewable resources and batteries has not been really worked out. A lot of assumptions we have, in what we cover this class really doesn't carry over when we have something like wind and batteries. So, there's an open and quite exciting problem for all these system operators. As how do you modify this type of market to play better with batteries and renewable resources, right? But as far as the harder market nowadays is just this for clearing supply and demand. Okay. So let's take a break now, and we'll come back at 10:30. We'll look a little bit at bilateral trading, then we'll do the review for the final. Okay, all right. So let's get started again. So we'll look at basically for the second half, we'll just look very briefly at the bilateral trading. Okay, so bilateral trading basically comes out because pool trading is still a little bit unusual form of market, right? Because as a buyer and seller, you almost never even have the idea of who else is in the market, right? So all you see is this central platform, and you don't see anybody else in the market, right? Where bilateral trading is much more classical, right? You as a buyer and seller negotiate with one another. You come up with some kind of agreement between these parties, and nobody nobody else is involved basically. Right? You can form whatever contract you want in whatever form of agreement you want. In this bilateral trading, and basically bilateral trading, there is no official price, so there's a lot of bilateral trading going on. There's no meaning talk about official price. And the good thing about bilateral trading is basically you can have very customized long-term contracts. You can have super customized long-term contracts. You can negotiate between the parties. You can have different durations. Okay. So the advantage with this kind of thing is it's a fixed contract. Right? So basically you have a longer term fixed contract, and this reduces uncertainty for everybody involved. Okay? So it's a very fixed term contracting. The disadvantage, the bad thing, the disadvantage is it's hard to negotiate. Okay? So it's not often easy negotiating a long-term contract between the seller and buyer. Right? So this only works well for large amounts of energy. Okay? So this only makes sense basically at the end of the day when we have lots of gigawatts of power exchanging hands. Otherwise, the cost of negotiation is very high. So very hard to come up with this sort of financial and legal agreement over a few years. Right? So it's not trivial. Right? So whether you do bilateral trading or you do pooled market, and really nowadays what we have is just a mixture of that. So the financial market for power systems is getting very sophisticated, and there's bilateral trading going from decades. There's bilateral trading between parties with decades of agreement to people who is just in the very fast power market. So both skills happen, and really, it's depending on where you are, depending on the type of customers, the type of generation, there's a lot of different financial products that are out there, and so getting a little bit sort of hard to track with for system operators, because it's a little bit harder for them to track what's actually out there, and all this sort of different reasons people can have. So if you look at sort of the power system market, it's actually quite a active area, both in the practical side, when people are trying to come up with new markets and new agreements, and the theory side of what to do when there are understanding what are the correct ways of trading and selling energy. Okay. So for this class, we're just going to look at we're just going to stop here with markets, right? We're going to with the rest of this is beyond the scope of this course, but something to think about. Right? So the actual, the financial side of the system is very much tied to the physical delivery of power, and that makes a lot of things interesting of how the market works. So any questions about the power system market in general? Okay, so if not, let's look at the final, right? Let's say look at a few things about the final and look at where we are. So let's say look at the final. So this is on the 16th, next Wednesday, I think. Yes, so this is next Wednesday, the 16th. It's take home. Let's say we're gonna go from 9 a.m. to 11:59 p.m. Okay, so similar format with the midterm. So it's a take home. Again, everything is open except the communication between you guys. So as long as there's no communication between each other, then it's open everything. You can use whatever tools you want to use. Okay, so it'll be 2 office hours. So all this is on the course website, so you don't have to copy this down. But this is just going through the logistics, 2 office hours. There'll be 11 a.m. to noon, and 3 p.m. 4 p.m. Okay, so try to take a look at the final. Try to, if you have questions, longer questions, try to come to the office hours. Other than that, you can email me, but there's no guarantee I can reply your email very quickly. Within a few, there's no guarantee I can reply, say, your email within 30 minutes or something like that. Right? So you want to take a look when it's first posted, and try to make 2 office hours if you have sort of longer questions. Okay? Any issues with the timing of the office hours, the timing of the final? Okay, so there'll be. So we haven't decided on the number of questions, but it'll be shorter than the midterm. So it'll be shorter than the midterm. Also, so let's look at the topics. So topics goes from the Y-bus matrix. All right, so you still need to be able to write down the Y-bus matrix we're asked, all the way to unit commitment. All the way to unit commitment, right? So this is the range of topics we'll cover in the final. So again, using software is allowed as long as you show your work, right? As long as you show your work. For example, what you cannot do is say something like, "Oh, I typed this unit commitment problem into a solver, and this is what the solver tells me," right? So that's not okay. What you can do is you say, "Oh, this is a linear system of linear equations, and I use Python to solve the system of linear equations." Right? So that's okay, right? But you still need to show your work for this kind of thing. And so let's look a bit closer at the topics.
Professor?
Yeah, go ahead.
You mean the Y-bus matrix, you're talking about the mismatch equation and how let's do the last one approach by the several of the
No, not necessarily. The Y-bus matrix just say, can you write down the Y-bus matrix, right? So you still be able to.
You mean the
so for example, I can give you a system like this. Why do you draw this way? Okay. So I can give you a system like this. I can write down let's say the line emittance, say 1 minus j, 0.2, which is making up numbers, minus 0.5j, minus 2j, something like this, right? You'll need to be able to write down what this Y matrix is.
okay.
So that's by knowing what the Y-bus matrix means.
Okay.
You have to write it down. You have to be able to write it down, what this is. Okay, so this is something that can be on the final. Right, on the midterm, you saw something like this. On the final, you may see this again. right? Because we may be doing, power flow instead of voltage and current calculation. Okay? So this is Y bus matrix. You need to know the power flow equations. You need to know the power flow equations. Okay, so for example, you need to know that Pi is equal to some function of V and theta. You need to know the Qi equal to some other function of V and theta. Theta function of V and theta. Right. So these are the things you have to know. To know where to find these equations, right? Be able to write down these equations. For example, if I give you V and theta, you should be able to compute the P and Q. Okay? Compute P and Q. So this is both, right? This is both for the bus injections and line flows. Okay? So you need to be able to compute, for example, the total injection at a bus, or I can ask what is the P and Q flow on a line. Okay, so both are possible questions to ask. Both are possible questions. Okay, so any questions here about power flow equations? So you have something to clarify, please ask, right? So please ask. This is sort of the last time, I guess, other than Friday, we'll talk before the final.
Professor,
Yeah.
I mean, both for the bus injection and the line flow, and what's about the line flow? I mean, the power flow equation.
So for example, I can ask you this question, right? So let's say still given this diagram, I can ask what is the P and Q here, right? I can ask at this bus,
Yes.
or I can ask how much P and Q is flowing along this line.
It's just a subtract between the two nodes.
No. It's not subtracting the power injection between the two nodes. Yeah, it's definitely not subtracting the power injection between the two nodes.
How to do that?
Okay, so how to do that? So if you look at the power flow equations, you should know how to do this, right? You should.
So we got the power flow, we got all the voltage at each node and all the angle at each node. So we can get the voltage drop in this line. So that's subtraction of the voltage. No.
Okay, that's a complex voltage, right? You can get the complex voltage difference, yes.
And the line flow, we want to guess how many the power and the real power and reactive power flow through this line. I think this is just subtraction between the two nodes, the real power and the reactive power.
What do you mean subtraction between the two nodes?
Two paths.
Like they're connected to other things, though.
Okay.
Yeah, they're not. I mean, each of them is connected to everything else. So I'm not sure what subtraction means in this context.
Okay. So how we just solve the question like the line flow?
So how do we calculate the power flow equations, right? Power flow equation is a summation. So if you look at the power flow equation, it's a summation of line flows out of that node.
Yes.
Right. So this particular line flow is one term in the summation.
Okay.
Right. So, but that's something. So, but still, that's basically if a question like this is testing that. Do you know it's one term in the summation?
Okay. So, thank you. It's just one of the summation, so we only need to calculate one.
Yeah. So if you look at the power flow, right? So let's be a little bit clearer about what this power flow means. Pi is a summation of Pik from all k that's connected to I, right? All the bus that's connected to I. Right, so this is basically look at the power flow equation, this is how the equation is written. Right, so line flow is one of these terms. Okay, that's what I wanted to.
Yeah.
Okay, so those are the power flow equations, right? So again, not only need to know where to find the equations, but understand how do we derive them, where do they come from, what does each term in the summation mean, and things like this.
Okay. And the bus injection is a generator injects into the bus.
And bus injection can be a load, right, or generation.
Okay.
So just a net amount of injection.
Okay. Thank you.
Okay, so this is one thing you may need to know. Okay, so another thing, for example, so that's the power flow equation. So know where to find the power flow equations, know how to compute them, things like this. So we will not have there be no how do I say this? There will be no questions like given PQ, find V and zeta. There'll be no power flow equations, no power flow problems. So that's homework question, that thing we did. I think on the final, we have that again on the final. I don't anticipate that working out too well. Okay, so there'll be no question like, given PQ, find V and theta, but there may be a question like given V and theta, find P and Q. Okay, so that's fine. Okay, so that's something we may or may not have in the final. Other questions about this? Okay, so there's after that, we have optimization problems. All right, so the optimization is mean, let's say, summation of the cost subject to a bunch of constraints. Or something like this. Okay. So then here we can ask questions like, you have first, of course, know how to solve these. Know what the multipliers mean, right? Things like this, right? So these are basic principles we need to know. There could be multipliers, there could be, we can ask a question, just say, okay, solve for x. We can ask you, find the Lagrangian multipliers. I can ask questions, that have to do with interpretation of the multipliers. Right? These are questions that can be asked for optimization problems. Okay. So again, right? So if you look at this, for inequalities, right? So definitely you see some kind of question that have to do with inequality constraints. Okay. So the way to solve for inequality constraint is the following, right? So for inequality constraint, as you firstly you solve without inequality constraints. Then you guess the binding constraints. Okay, then you guess a binding constraint from the solution of the unconstrained problem. Okay, so normally the problem will start at being away. Now we solve the unconstrained problem. One of the inequality constraints will be violated. It's sort of obvious what's the next step to try this. Right? If you solve it, for example, generator 1 is generating more than its upper bound. Then sort of the obvious thing is to try to the next guess is, okay, generator 1 is generating at its upper bound. Let's resolve the problem with that as the new equality constraint. So will be inequality constraints, but the idea is not to make a big table and try every combination. So solve it with the equality constraint satisfied, no other inequality constraint, then guess the binding constraint based on that. The problems will be set up in a way that's nice enough that you don't need to guess too many times.
Professor?
Yeah.
So when we finding like the binding constraint, so do we need to calculate the constraint as the multiplier, like the mu1 and the mu2 for the inequality?
You have to compute that, otherwise you cannot solve the problem.
Because if first time we just solve without inequality, so we find the lambda, so we figure out what's the binding constraint. So we still, so you mean we still need to finding like the mu1 and mu2 in the inequality.
But when you're solving without inequality constraint, there's no, the mu's are 0, right? You're basically assuming they're
Yes.
0.
Yeah.
So I'm not sure what, again, finding that means.
And also, what means the multiplier? What does this mean? Because I know the lambda, like the unit is the dollar per like the megawatt. And since we know the P1, P2, P3 after the calculation, and we just put into the equation for the C equal to the P1 and the quadratic equation. So yeah, so we know the cost of the C1, but at what situation we need to use the multiplier?
There's many situations we can use the multiplier, right? So in one of the homework questions, you see you see this kind of problem, you know, right? So multiplier, as you said, has interpretation of dollars per megawatt hour or per megawatt.
Yeah.
Then there's many economic questions or many questions that can be asked based on this interpretation.
But like what we, because we only need to calculate C1, we only need to know the value for the P1. And for the C2, we only need to need the P2. So we know the cost of, and for that's the marginal curve. But where should we just use the lambda? Like the lambda multiplied by what?
Like the lambda multiplied by what? Like for example, you can have a question like, you know, given this many generators, this is a load, solve the problem, right? Get some lambda. And then part B can say, okay, there's a new generator with marginal cost X. Is it worthwhile to put this new generator in the system or not? That's an example where you can use the multiplier. If the marginal cost of the new generator is larger than the multiplier, then the answer is no, you don't need the new system in the system, right? You don't need the new generator in the system, right? You don't need to do any more calculation.
Okay.
There's many questions like this I can ask. I mean, yeah. So when you study, you think about, you know, try to think in your mind, what are the things that can be asked? That's a good way to study for this exam, right? So now the calculations will not be overly hard, but you get questions around, you know, what these calculations mean, right? So yeah, you get, you know, you get a question what these calculations mean. You can get a question of saying, you know, asking around the multipliers. You can get a question has to do with the fact that, you know, the multiplier means a price, right? So these are all questions that can be asked.
So what's the unit for the cost? The C here.
Dollars, right? Dollars. Right, so if load is in megawatts, it is in dollar, and the lambda is in dollar per megawatt. Any other questions around this? Okay, right. So this is something to think about, right? So if you're doing the homework and taking you very long to do the homework or to solve this optimization problem, maybe it's something to practice, right? So you see this on the final for sure. Another example, another thing we can ask, right? So something will be like, then we can look at unit commitment. All right, so unit commitment, right? So here is the way we do it is you need to be able to make a table. Right, so this is the status. So about the generators, this is, the generation level, cost, things like this, right? So the way we solve it is that you need to be able to make this table. You need to recognize when it's feasible, when it's not feasible, things like this, right? Things like this. So sort of very, just know how to do how the homework's done. For this, know the difference between startup cost and no load cost. Right, we may have something like shutdown cost. Right, so there's sort of different costs in the unit commitment problem. Right, so the startup cost and shutdown cost only occurs when the status transition, whereas the no load cost is always there. Right, so you need to know this, understand how these may impact the solution, right? May impact the solution. How does changing the cost impact feasibility? Does changing the cost impact generation levels? Things like this, right? For the unit commitment. Right? So for unit commitment, be able to make a table and then understand if some of the costs change in the system, what changes, what numbers in the table change, things like this.
Professor, I have a question about that.
Yeah, go ahead.
So I know what the no load cost is, but have we seen a problem with startup and shutdown costs yet?
Well, I've definitely seen that during class, right? Over class. In examples during class, I've seen it. Right, we had the startup cost. The shutdown cost is not very different than that.
Sure. So just for clarification, then I think I talked to you about this in a different lecture, but the startup cost is going to be a separate like value outside of the cost equation.
Yeah. So so the cost equation, let's say this again with making up numbers. So this is a no load cost, right?
Right.
And nothing here has anything to do with the startup cost.
Okay. Yeah.
The startup cost needs to be listed differently. For example, this.
Is it going to be listed like that, where it'll be like startup cost is equal to, or is there like some variable that denotes it or anything like that?
No, we stated in plain language, like startup cost is this.
Okay, wonderful.
Yeah.
Thank you.
Yeah, there's no variable. So we don't have a variable for startup cost. So the question that has startup cost will read as startup cost for generator A is $1,000, something like this. Yeah.
Okay, perfect. Thank you for the clarification.
Yeah, no problem. Yeah, so these are the questions you can ask in the office hours through emails, right? So clarification like this, definitely I encourage you to come office hours on that day or through email. Right? So something a little bit more difficult to ask is last time somebody showed me a solution in office hours and said, okay, can you tell me if this is correct or not? Then that's something perhaps not asked, right? But use the office hours and email communications ask for this kind of clarification questions. And please do ask you, right? If you don't know, does this number mean this or mean that? That's, please ask about those. Okay, so this is basically at the end, right? So this is where we stop. So in the market, we probably won't have a market question in the final, right? Since we haven't really done any homework on that. But anything, we have done in the homework, right? Anything similar to that, or, think about all the different ways the questions can be asked, could be potentially on the final. All right, so any questions, comments? Okay, so if not, then we'll end here today, right? So good luck for the final. Good luck with all the other finals and projects. And so I'll see you on next Wednesday then for the final. Okay, so no questions. We'll end here today.
Professor,
Yeah.
can I ask a question for the homework?
Yeah, sure. Yeah, for homework questions, we can go over the homework. Yeah, go ahead.
So I'll do the question 2 and the homework 8 question 2.
Sure.
This part I calculate the let me see. I calculate P1, P2, P3, and the lambda. And I figure out there's a banding on the constraint for the
Okay.
and because question 2 they gave the power like the P1, P2, P3, P4. And I realized there's a bending constraint on the P1 and the P4.
Okay.
And the P1 is there to be maximum be 200. P4 is the minimum. Minimum is 240. So after this one, how should I like the calculation to finding the multiplier for the P1 and the P4?
Those are just the mu's, right?
Yeah, mu. It's not 0, so.
Yeah, so you solve the problem, the mu comes out, right?
It doesn't come out because I put the equation here. For the beginning here, I just put the L equals to F plus the lambda times 800 minus P1 minus P2 minus P3 minus P4. And I figure out the P1, P2, P3, P4, and the lambda. In this situation, P1 is larger than the constraint, and the P4 is smaller than the constraint. So,
yeah, that I understand, but so basically what you're saying is you have we have a mean of 800, and right, you're saying you're guessing basically P1.
Yeah. So P1
50 or 200, which one?
Yeah. So I just guess the P1 equal to
200.
200.
240 equals P4, right?
Or 240.
This is your guess, right?
Yes.
Okay, so when you solve the problem, you basically have a Lagrangian mu1 P1 minus 200
Okay.
mu2 times 240 minus P4, and the Lagrangian. So this is sum of the cost pluses plus lambda 800 minus P1 plus 800 minus P1, P2 minus P3 minus P4. Right, so you have this derivative equal to 0.
Okay.
So you have the mu as a variable, so it comes out.
Okay, in this way we can find the lambda and the mu.
Yeah.
And for example, if we find the lambda here, let's say lambda equal to the 36.8.
Okay.
So
Okay.
we know the cost for the P1 is the quadratic function.
Mm-hmm.
And for the lambda here, so why we calculate the lambda? Like what lambda can be used in the further question? Like lambda times the P lambda.
Payment, right? So I can ask, how much does the generator one get paid?
Yeah, generator one get paid by the
Lambda times the P1 that, the P1 is actually generating, right?
generator get paid.
Yeah.
How much should the customer pay?
Lambda times the total load.
Lambda times the total load is the customer pay.
Yeah.
What's the C is just the cost for the curve for the generation. It's nothing to do with the payment. Yeah, directly.
No. The lambda is determined by the parameters in C, right?
Yeah, I mean the C.
The lambda comes out because the different coefficients in the cost function C.
Okay.
For example, if I change the coefficients, the lambda will be different, right?
Mm-hmm.
So lambda is computed based on that.
So when we do the unit commitment, like the unit commitment of how many power be distributed for the generation 1 and our generation 2 or generation 3. So we'll calculate the cost. This time the cost is just the C.
Yes, because we're minimizing cost. Yes. So here we're also minimizing cost.
So,
I mean, both are useful. Both are useful. Right?
Okay.
The cost in some settings we care about the total cost. In some settings we care about the clearing price. In some settings we care about both.
All right, thank you.
So I actually have a question just about minimizing a function using a Lagrangian. Should we be, so once we find a solution, should we be, like, do we need to check to whether it is a minimum or a maximum? Because I was thinking just mathematically it could be either, right?
Yeah, so right, so that's a good question. So just for our case, we're dealing with convex problems, convex optimization problems. So there's a guarantee that there's a unique stationary point of the Lagrangian, and that's a minimum. So in practice, it's much more difficult. You need to check, and often it's very difficult to say what it actually is. But just in case for us, since the problem we're dealing with, the technical term is convex. And so for this convex optimization, you can be sure that the stationary point, basically when the gradient is 0, is actually a minimum. That's a good question. But in general, it's tough to say what it is. Or for us, there's just the problem set up such that there's only the minimizer.
Thanks.
Other questions?
The question about number 1.
Sure.
Just to clarify, so you kind of talked about this during lecture today, but
Right.
You had discussed how solving it with ignoring all the constraints, and then part B, asked to solve ignoring the inequality constraints and then considering all constraints. So
right.
are we referring to all the inequality constraints as the 7 is less than x1 is less than or equal to something else, right?
Right. So right. So
what
so
is
normally, yeah. So normally the first step. So this problem, a part is us ignoring all constraints. That's sort of a trivial problem. But the way to guess which inequality constraint will be binding is to first solve the with the equality constraint.
right? Okay, and the equality constraint is what is the s dot t dot denoting?
Subject to.
Okay.
So in English, this is minimize the subject to the constraints.
Okay, so that's the equality constraint.
Yeah, that's the equality constraint.
Okay.
No. So subject to includes all constraints. It's just a way of sort of inverse. Right? So in English, this reads as minimizing this function subject to a bunch of constraints. It just when these problems are sort of typed up, it means this s dot t dot subject to, and that means sort of all constraints is included.
So then how would part B be different from my answer to part B be any different than my answer to part C?
So part B does solve the problem specific, ignoring all the inequality constraints, right? So you may get a solution that adds up equal to 9.666, but does not satisfy the inequality constraint.
Okay.
Yeah.
So you're pretty much saying that you're considering the subject to equation in part B, but not the inequality equations, and then in part C you have to do both.
Yeah, in part C you do all the constraints.
Okay. Sweet. Thank you, Professor.
Yeah, no problem. Any other questions?
I guess I can ask a question real quick.
Sure. Yeah.
So in the previous slide for the review, when you said for the unit commitment, if a cost changes in the system, and the question was what would change? Well, wouldn't technically everything change, because then that would change our economic dispatch problem, meaning we'd have to pretty much recompute that, which is a pretty big.
No, right? So that's the point right now. So for example, if I change the no load cost, will the generations level change?
Okay, makes sense. Sorry, I thought you meant like the total cost function.
Yeah, so I mean, so this table has many cells, right? So changing some cost changes some numbers in some of the cells. So it's important to know what remains unchanged for some changing of some cost.
So I guess just to clarify, when you say changing the cost, do you mean the no load cost? Because the coefficients, for example, 5 and 0.04 would still stay the same. We just changed the 100.
I mean, that's one example of changing a cost and asking you to recompute the problem. There are other examples. There are other things I can do that's sort of similar. That does not. I can say change this, but it actually doesn't require you to just redo the entire table. There are other examples.
Okay, but if we were to change, for example, the coefficient 5 or the coefficient 0.04, then we would have to recompute everything, because that would be in, once we take the derivative, that would still be included.
You will have to recompute everything when the generator is on, right? So there may be example when it's infeasible. So that does not change feasibility.
Okay. Thank you.